Hello everyone, thank you very much for giving me the opportunity to send my presentation and the video record for the International Symposium on Infrastructure Development. This is Omar Altawani from Ankara University, Turkey, presenting our work on behalf of my colleagues. We start with the first one, entitled Evaluating the Applicability of Conditional Bivariate Probability Function for Air Pollutant Sources Identification. Before I go on with my presentation, I would like to express our solidarity with the Indonesian people and all the people who suffered from the recent tsunami, and we just promise them that we will try our best to work on reducing the impact of such natural disasters. So I will pause this presentation for 1 minute, then I will continue. Thank you very much. I'd like to introduce my colleagues that work with me for this piece of research. It's out of a project that is conducted with the University of Petronas, Malaysia. So we have the Dr. Abdul Latif, Dr. Ali Aid from Morocco, and Dr. Trinos Gumo from Johannesburg, South Africa. Briefly try to introduce the topic here. There's a large number of pollutants around the monitoring stations that we try to make the identification process more easier. As you know, in Southeast Asia, especially in Indonesia and Malaysia, the most effective natural hazard is the air pollution. So here we have some issues about the large number of pollutants around the monitoring stations that is installed already to monitor this man-made hazard. So it's make the identification process more complex, such as the distant and large emitters sources around the receptors that cannot be efficiently identified using a basic bivariate plot for most of. So the modeling of the receptors to identify the characterized emission sources is typified by difficulties like incomplete information of the sources and the difficulty in modeling boundary layer processes. So we have to investigate how to prevent making the arbitrary and uniform decisions on how to extract and analyze the main emitters among the multiple sources in anthropogenic hazardous prone areas. So here the main objectives of this research is to utilize a conditional bivariate probability function CPPF to identify sources of pollutants emissions, and to use the CPPF with hourly pollutant concentration value such as the SO2 and NOx and CO and particulate matter 10 to be plotted as a function with the wind direction and wind speed in a polar coordinate system, and also to use the R programming package which show the durability and efficiency in terms of data size, processing time to implement the mentioned technique. Also, we would try to simplify the technique in order to aid the air quality monitoring agencies and other stakeholders to link the identify the pollutants, to know the emission sources, and finally to use a GIS in mapping the existing pollutants and take a general insight about how to help in validating the potential sources of the air pollution. Here the study area actually is taken from Kuala Lumpur, Malaysia. So the data collected actually from the 1st of January to the end of 2016. And this station, it was located in a complex and high pollutant sources region, north and east part of KL city center. And it's the best place to test this methodology because the area it's surrounded by complex industrial area, which is chosen to study because it's easily detected by distance resources, and that is because of the flat terrain of the area that the station is located in. So in general, you can see that the major industrial pollutant sources are delineated by a circle radius of 5 km surrounding the receptor. These sources include food, beverage sectors, automobile maintenance and services, chemical industries, as well as the complex road network. So the map here is mentioned to the station here, and you can see that all the pollutants mentioned around, most of them in the southeast west of the station, and some are located in very close distance on the north and northeast. Here it's the mean value of the NOx and PM10 and CO2, SO2 and CO. As you can see from the pollutant windrows, that's the pollutants coming from the southwest, and it's vary based on the type of the pollutant species. So we can see too much SO2 is coming from the south and also from the southwest and the north east, and that it's coming also with the PM10. But as you notice here, there is no indicator to where those pollutants coming from, especially with the CO. So we can see there is a limited number of pollutants in the northwest, but here we notice also some is coming. So it was the traditional way to identify the sources, which it's really confusing, especially in the PM10 now, when you see how much is the diffusion of the sources. It's all around from east to west, in the southern part. So we will try in this research to limit it and to focus those effects in CBPF technique. Here we notice that the frequency of count by wind direction in the figure 4, it's giving us exactly the wind speed and direction for the station. So you can see the colors vary based on the meters per second. This is the speed for the wind, and as well as the direction. So also we can notice now the wind, the strong on the fast wind is coming in the direction of the pollutants, while the area that we have less pollutants, that the wind it's slow there. Here it's the summary plot, and we notice also the different value for the pollutants along the year. In the methodology, we use the R package MICE, which is the multivariate imputation by chain equation. This method we use to impute the missing data. Usually, when we collect a record for 1 or 2 years, they will be missing data around maybe 1 or 2% of the data for like a month or a few weeks. So we need to impute this data before go ahead with the programming or with the analysis. So mainly the CPPF is depend on the number of samples in the wind sector, also the pollutant concentration, with the threshold value of high percentile of the concentration and the total number of samples from wind sector, as well as when we include the additional parameters like wind speed or temperature, the wind speed interval will be integrated with the equation. Here with the CBPF identified, the nature of sources become more visible, especially the one that have a significantly different wind speed or temperature or humidity dependencies. So we can understand here we will try to use the wind speed or the temperature or any external factors to focus and limit the direction of those pollutants, connecting them to the main sources. The result, actually, after using this 1 year data, using all the parameters, which usually find that the PM10 is the highest value. So we use the PMM for the mice package to impute the missing data, and we have like just 2.8, almost 3% of missing in the NOx, but the rest of the data it's within less than 1%. So we don't have a problem here with the uncertainty, because most of the imputation techniques work very fine with the data less than 5%. In figure 6, we notice that behavior doesn't specify clearly, as we mentioned, the limited resources. So this is referred to the most surrounding industrial area. So the figure 6 here, as we mentioned, that it's still confusing when we link to the figure 1 here and we see all the pollutants around. So usually so far, this was the current technique of identifying the sources. Also in the figure 6, they show that the wind direction is not the only indicator of the pollutant source's direction. It's equally possible to identify at least 2 sources type with the different dispersion characteristics. This information is validated by table 1, showing the summation of pollutants from the 4 main direction zones, even though figure 6 provide minimal information about these sources. On the table here, the 4 directional zones in table 1 show the highest value of all the pollutants registered from the northeast. You notice here, especially for the BM and the NOx. So here, this side, which it has some closer pollutants group, because the closer one, it is showing the highest impact, which is it's a food processing and some industrial park within 1 kilometer. So that is logically it will show highest pollutants rates. Here the figure 6 actually also it's reflect the uncertainty. So when we have the low uncertainty and the upper uncertainty about the sources, that it will need more data about those areas that it's mentioned by the upper uncertainty and the lower one. So here is the main prediction, but the others that is showing that when we have some uncertainty here, we need to have a solution or to allocate some network to figure out what is making the values high. We notice here in figure 7, this is actually ideally the CBPF plot, which you notice here. We categorize the value of the NOx based on the 10 percentile from a specific range to delineate the sources. So the sources, some of them it emit within like 5%, 10% of the pollutant, but while the others, the range of the emitters between 50 to 60% of this pollutant. So the technique mostly depend on the categorizing the pollution or the species like the NOx into 10 parts. I'll take the percentile of it. Then within those range we try to find each emitter with this specific value. So we found 10 value for each species, and then we just choose the one that it's mentioned to the each emitter. For example, if you see here for the northeast part with the 4 pollutants, the NOx, it show the first percentile, it's mostly come from the northeast. Also with the value of PM10, which is from 35 to 38, so it's the API, and the other value from the CO, and you see it's very small amount, but it's successfully detected. So here you might just see this one, the CPF of the PM10. This is the real value. This is the real value. We want to see, also check the southwest. We see also a specific range for the SO2 and the NOx, the PM10 and CO1. It is also mentioned with just a specific range. If you take all the range from 0 to 100%, you can see them, they are showing you different directions. So this is a study, a pilot study. We took already like a supervised analysis. We have already the source of pollutions, and based on this we tested our model, which kind of range that it can show us the emitters, or is it successfully can show us the emitters that it's already located on the northeast and the south west. So yes, the CPPF technique show us successfully and point successfully to those sources. Also, it's interesting that to notice 2 more sources appeared emitting PM10 and NOx with respect to the southeast that emit in the same amount and wind speed. That need further investigation actually to produce standard emission table refer to each pollutant, regardless of low concentration value and limited data that we have used now with just 1 year data. Now these sources are clearly visible when we analyze using the CPPF approach. So as we mentioned, that some even though the radius of the study area source location are up to 5 kilometer distance, the topology did not affect the depletion of these sources, similar to the finding from the area studies. To sum up, in this study, we focused on deriving more details, more sources, on identifying the air pollutants sources by combining 2 approach, which is CPF for source direction identification and the bivariate polar plot for source dispersion modeling. The basic independence for those 2 methods are wind speed and direction. The distant and large emitters sources in the northeast of a receptor were not identified using the normal common methods, while using the CPPF comprehensive plots produced using the pollutants that to be constrained in the low and high intervals of the species, especially to the northeast and southwest of the receptor. NOx sources in the northeast couldn't be identified by the CPF, while it's disaggregated clearly using the current technique. Further information regarding the main industries types and annual emission needed from every industry to identify the exact higher emitters among those industries. Moreover, wind directions might come in a circular pattern, not always in one direction, that dilute and give wrong image about the pollution sources. This is need to be considered in the future research. And for comprehensive source identifications, future work will consider more receptors, annual resources, emissions amount, report, and road network, which is also one of the most important and effective emitter. Moreover, ambient temperature and humidity dependence will be included. At the end, I would like to mention that this research is a part of the financial support from UTP Strive Research Grant project. Also, we are grateful to Department of Environment Malaysia for providing the air quality data used in this study. Thank you very much again. This is Omar Al-Thwaini, and please, if you have any questions related to this research, send me to my email that is mentioned. So terma kasih atas perhatian Anda. Thank you very much. شكرا لكم على الإصغاء, and I wish a very good day for everyone.